right, folks, I think it's about time to get started for today. Welcome back to those of you who survived one lecture. We'll start with a few announcements and then get started with our class material. I'm going to quickly glance at my laptop and make sure that it's actually picking up the audio because several of you asked for recordings. Yes, okay, fantastic. Right, so let's see, we're in the second lecture of 68410 here. I'm guessing because I put a recording on the internet, now half of the classroom has dropped out, but that is life in the city here. But in any event, I'm glad that you guys all came. So a few announcements, then we'll get started with like actual math today, which is I'm excited for. Right, so in terms of announcements, first of all, regarding recordings, you can see that there's a complicated situation here. This is extremely unstable. This is my home-brewed recording system. It is your responsibility to know whatever happens in this classroom, regardless of if there is a lecture recording and when it might be posted. That is this course policy. These recordings are for backup purposes only, and you cannot rely on them. Yeah, if I make any other policy, like come or don't come and watch it online, then I know what'll happen is the technology will fail, and then I'll get the unhappy email that like, oh, you got to remove this homework problem because I couldn't see it in class. But that is not the case. You are responsible for anything that happens here. If you don't show up, it's at your own risk. Any questions about that? Fantastic. I had some other threatening thing to say, but I forgot. Oh, right. Other than that, homework 1 has been posted twice. So if you downloaded homework 1 in the first couple hours, I beseech you to erase that file and then download it again. Your instructor is really bad at Git, hit the wrong thing, and then posted the solutions to the homework instead of the homework problems. You guys, this is a graduate level course in geometry, which is completely optional for every single person in this classroom. If you cheat, I mean, we always say that you're cheating yourself, but like really that's the case here. Like it's just dumb to cheat in this class. So just don't, like just drop this class if you're thinking of cheating. It doesn't make any sense. But of course none of you would do that anyway because you're all upstanding MIT students, and as we all know, no MIT students have ever cheated on a homework or exam. Any questions about that? The due date is already on there, and by the end of today's lecture, you'll have more than enough material to do at least half of the problems. Really all the problems. I mean, the problems are basically just calculus, but you'll get the more background as we move forward. Okay, yes?
You said there were 5 homeworks for the class altogether.
Uh-huh.
Do you think the first homework is roughly representative of, like if we really struggle with the first homework, is that a really bad sign? Or like if the first homework is super easy, does that mean the rest of the course will also be super easy? Or
No, you will suffer. I'll find a way.
Okay, cool.
No, yeah, so the question was like if you're like really struggling and having bad news town on the first homework, like are the rest of them going to be equally hard? I mean, at the end of the day, this is a PhD qualifying course. Like the homeworks are intended to be challenging. If you're having trouble, you need to kind of decide what kind of trouble. There's just like general struggles. There's I am missing background material for this course. So all I can offer you is that, of course, you can come talk to me and we can kind of talk through that. It's hard to make a one-dimensional projection, but I do think the homeworks are similarly structured to each other, and they're all written by the same guy. So, like, you know, make of that what you will. I'm giving lots of non-answers today. Anything else? Any other questions that I can evade? Okay, fantastic. Well, in that case, we will get started with the technical content of 68410. So today we're going to have a lecture that's like sort of review and sort of new stuff. That's our plan. So we're going to start out with some concepts for linear algebra and calculus just to kind of get our brains warmed up. But while we're doing that, I'm going to introduce some of the really annoying notation that geometry people like to use. I personally hate it and try to avoid it in my own research, but the reality is that if you go out into the world and start reading many geometry textbooks, as I anticipate you all will, sadly you need to be able to parse this kind of thing. So I've made it my own responsibility to translate this course into the notation that I hate in order to force that upon all of you. So today we're going to have a bit of an introduction to the sort of clunky indexes and ways that people in this area of math tend to think about matrices and vectors and all that kind of stuff. And this will come back to haunt us many times in this course. When we talk about Laplacian operators and derivatives, when we talk about exterior calculus, all of these are tools that make use of really messy things in coordinate systems. And in some sense, this makes sense, because like geometry is all about the stuff that you can do without a coordinate system, right? And so somehow what happens is when you start like putting charts and maps and things into geometry, the notation gets messy, because it's somehow not a natural connection. But that said, oftentimes we're forced to do that kind of thing. So we're going to have our outline for today look something like the following. So first, we're going to talk about linear algebra as kind of a subset of geometry of flat stuff. In particular, we'll go back through like matrices, vectors, all that kind of thing. But my goal in talking about matrices and vectors is already to just like put a little inkling into your mind of why maybe your undergrad linear algebra class elided a few details that are going to be really important for us when we go back and reconsider measuring lengths and angles in the Riemannian sense. And then after that, we're going to talk about optimization, which is one of the main tools that we use in geometry. In particular, a lot of the techniques that will motivate in this course are going to start out with some optimization problem, like find me the shortest path between these 2 points. Notice it's an optimization problem, right? Minimize distance over the set of curves. But geometry has this weird flavor to it, where your optimization variables aren't just numbers, they're like shapes. And so in today's class, and hopefully the second half, I cut a lot of content relative to last year because I never get there in time. We're going to talk about what it might mean to apply the machinery from calculus class to optimization for objects like functions and curves. Right? So usually in calculus, you talk about like find x minimizing f of x. But if I want to talk about like what it means for a curve to be the shortest length curve on a surface, we need some additional kind of operating system for doing that. And in particular, we're going to learn a little bit about variational calculus. Okay, so that's going to be our plan for today. So if you're like worried that this is boring linear algebra view, you're right. But then at the end, we're going to like suddenly drop onto you a totally new approach to math problems you're not used to. And it's homework 1, like literally problem 1A on your homework is going to be to do a calculation very similar to what we'll do here. Spoiler alert. Okay, so let's get started here. Our first step is going to be talking about linear algebra and to introduce you to horrible notation that we all have Einstein to think for. Okay, so just as a bit of convention for this course, here's going to be our basic set of notation here. So we're going to think of most vectors by default as being vectors in Rn. But we're going to try to avoid using coordinates a lot because that's the thing that geometry people don't like to do. But in general, when I talk about vector, it really is fine to think of it as a list of numbers. And we're not going to worry about infinite dimensional spaces unless noted otherwise. So we'll use bold, small letters for vectors, capital letters for matrices, and this little T dude for transposes. Cool so far? Good. Here's 2 pieces of notation you've probably seen before. But just in case, I feel like sometimes in undergrad linear algebra, this fact gets passed by a little bit quickly. One thing you might remember is if we think of our vectors like column matrices, which is going to be our convention here, then the dot product between x and y can be written in the following notation, right? X transpose times y, right? So X transpose makes a row vector, right? Y is a column vector, and we all remember how matrix vector multiply works, right? Kind of like that. and so at the end of the day, this is a 1-by-1 matrix or a scalar with the dot product, and the phrase quadratic form just indicates I'm going to stick a matrix in between these 2 guys. Any questions so far? This is just notation to make sure we're all on the same page here. But the one thing that you might have forgotten from linear algebra is just that X transpose Y when X and Y are vectors is really just a dot product. Cool. All right, so that wasn't enough notation, so let's add a little more. And now we're going to start having notation that may differ from your undergrad linear algebra class a bit. In particular, vectors are these weird objects. Because we draw pictures of them and they look like cute arrows, but then we write down lists of numbers. And actually, identifying those 2 objects is something that we do intuitively. But in geometry, we try to divorce a little bit, right? Because, for example, if I take a surface and I like rotate it, it makes perfect sense to kind of rotate the vectors with the surface. But then all the coordinates like jumble around, right? So like the geometry didn't change, but the numbers we were working with did, right? And so to the extent that we can work with this like nice bold case V and not worry about the coordinates underneath it, the better. And we'll see many examples of that in this course. That said, if we need access to coordinates, notice I have made a notational decision, which I'm going to screw up in this class, but I tried to make consistent this year. I went through all the course notes like 3 times, which is we will use upper indices So this does not mean the nth power of a number v. This is the nth component of a list of n numbers. Does that make sense? And we're going to see why in a second. Those of you who have taken a geometry class in the math department probably know where I'm headed with this. Okay? If you haven't, that's great, because we're about to cover it. And in addition to that, you might remember the standard basis vectors. So this is like 1, 0, 0, 0, 0, and then 0, 1, 0, 0, 0, 0, and so on. And we're going to notate that with boldface E. Notice that the index is down here. Right? So we have a set of vectors with lower indices, and we have a set of coordinates with upper indices. So notice if I wanted to write my vector v in the standard basis, I could write it in the notation here, right? Because essentially ek is like picking out the kth coordinate, and then I'm scaling it by this scalar here. Does this expression make sense to everybody? I should pause for a moment. You're going to be awful bored in this class if this is if lost you, and it's okay if it has. Okay, fantastic. So the thing to notice in this expression so far is that there's an upstairs and a downstairs, and they match together and they get summed. That's going to be the pattern that we're going to match on a lot today. Okay, so that's vectors. And in our undergrad linear algebra class, we usually deal with two objects, right? Vectors and then matrices. If you dealt with tensors, you had a very fancy linear algebra class. I certainly didn't. When we talk about matrices in linear algebra class, I feel like there's two things that matrices get used for that kind of get smushed together, and we don't think about it carefully. And so I want to kind of call out that we see matrices twice in linear algebra class, and we're going to see that that actually is going to have really important bearing on how we write down our differential geometry later. So in particular, one of the very first things that you do in linear algebra class is you talk about linear transformation, right? And so that would be like a function L that we have on the top of the slide here. Right? When we talk about linear transformations, they satisfy two properties, right? Namely that L of x plus y is equal to L of x plus L of y, and that L of c, where c is a scalar, times x, is the same as c times L of x. Hopefully this is a familiar construction. My phone keeps buzzing. It's my mom. Okay. So, right. Where was I? So typically, one thing that you show in linear algebra class is that if you have a linear transformation, it can always be understood as a matrix vector product, right? And so that's where matrices sort of arise for the first time in linear algebra. And I thought it would be a little bit instructive to actually write down that identification a little bit carefully. And again, this is mostly just practice with notation and for me to remember how to write on a blackboard. So incidentally, I hate this classroom. I put in a request to change. MIT is slow, so like 10 years from now, I'll get the email saying what room we are going to move to. But for now, we're going to make do. And because we're filming, I'm further constrained to just this side of the room. So if you can't read something, feel free to stop me anytime. There are a lot of students in the back who could move forward. There are plenty of seats. Just putting it out there. OK. So let's say that I have a vector x, right? And based on the previous slide, I can always write x in coordinates, right? So this is like the sum over k of the kth component of x times the kth basis vector. I hear some chatting. Is there any question? Fantastic. So let's see what I can do here. So let's say I apply my linear transformation to x, right? Those of you who took my undergrad graphics class will recognize this calculation just in like souped up notation. OK, so now I can substitute in my form for x. So this is L of the sum x, k, e, k, like that. OK, now what do you think I'm going to do? Well, I kind of only know two things about L, right? That it splits over sums and scalars. So of course, this is the same thing as the sum over k of x, k, L of e, k, like that. That make sense? OK. So one of the kind of sneaky things that happens in linear algebra that I think goes by kind of quickly, but it's actually super deep, I think, is when I'm in a finite dimensional vector space here, what did I just learn from this expression about L? Like, the space of functions was really complicated. Like, there's a lot of functions out there in the universe. Are there that many linear functions? Not really, right? Because essentially, if I know this set of n things, then I actually can apply L to any vector, right? That's really what this is telling us. This is like a deep and thoughtful and interesting thing in linear algebra that just passes by like pew, when you're taking a class, right? That just these two properties alone are sufficient to like learn a heck of a lot about your operator. Moreover, we're going to do something which in our next lecture when we introduce the Frenet frame is going to get a little more complicated, which is the following. L of ek is itself a vector, right? And what do we know about the standard basis? I can write any vector in the standard basis. And one thing that I could do is write this vector in the standard basis. Does that make sense? So I apply L to each of the standard bases. I get some other thing. Could be rotated, could be stretched, whatever. And now I can write this thing in the same basis. So what does that mean? Well, I can say that this thing is equal to the sum over L of A lower k upper L E L. This notation makes sense. So this is saying I took the kth basis vector, I applied L to it, and now I'm going to, or capital L to it rather, and now I'm going to write that in the standard basis again, so I'm going to have an additional sum over the L's. Yeah? Notice I've made a choice to put the k down and the L up here, which is still consistent with the notation we've established so far. Any questions about what I did here? I know I'm writing kind of small, if nothing else. Cool. All right, so if we extract a little bit out of our sum, this thing is really the sum over k and L of x upper k, A lower k upper L, E lower L. I promise later in this course I'll stop saying all these letters out loud. Okay, so this is our expression so far on the left. And again, it sort of turtles all the way down. Anytime we see a vector, we're going to just keep writing it on the same basis. Okay? And there's one vector for which we have not done that yet, and that's all the way on the left-hand side. It's L of x. Yeah, so let's just give a new name to this object. Let's just call it y. So we'll say that this is equal to the sum over k of y, k, e lower k. So we're just defining y to be the coefficients of this thing in the basis. Does everybody understand this chain of equalities that we've done here? You might not know where we're going with it, but hopefully you see where they're coming from. Fantastic. So what do we know? We know that like decomposition in the standard basis is unique, right? So in particular, we know that yk is equal to the sum over L of this thing. And we know that for all k. Does that make sense? So if we think of A as a matrix and X as like a list of numbers, what did we just show? We showed that y is equal to A times X, where A is basically defined to be the thing where you write one guy in the other basis. So this is really where matrices come from. Do you see what we did here? Like the elements of this matrix are telling me I apply the transformation to the standard basis, and then I write it in the standard basis, and those coefficients are the elements of A. I think this is a calculation you've probably seen before, but you might not have called it out for what it is in linear algebra class. Okay? Cool. This stuff is fun. I love this stuff. But there's actually a second place where matrices also come up in linear algebra, and I think somehow they all get kind of glued together, but the reality is they're very different objects. So one of them is linear transformation, the other is inner products. So now, let's say I have a function g. Those of you who have taken remaining geometry class know why I'm using the letter g, but this is just foreshadowing. And g is going to satisfy a few properties that look a lot like a dot product, right? So it's symmetric. I can pull a scalar out of one side of it, and it splits over sums. Notice by symmetry, I could have put that property in the second coordinate also. Does everybody understand how g kind of looks like a dot product? Nods, acknowledgement of some sort? Like we're awake? Sweet. Okay, so what do you think I'm going to do? I'm going to write u and v in the standard basis, and then see what happens to g. Yeah? And we're going to end up with a very similar fact. Ugh. I warned you we're starting slow. Is this slow? I don't know if it's slow. Okay, so let's say I take u and v, and I apply g to it, like that. And I'm going to write u and v in the standard basis. So this is the sum u. I have chosen letters that are different than my notes, but that's OK. It's a recipe for disaster, but we'll see if I manage. And this is going to be the sum. I should write. For now, we're going to keep writing these things. V, L, E, L, like that. Right? And now, by just applying these four properties here, really just the first three, it turns out, but whatever. What am I going to do? I'm going to write this thing as a double sum. Yeah? So this is the same as the double sum over k and L of U upper K, V upper L, G of E K, E L. That. Right? So all I did was apply the kind of linearity here. Bilinearity. Everybody understand what I did? So let's say that I give this object a name. What letter should we give it? I don't know. How about G? This thing is indexed by K and L, but if we're pattern matching based on the calculations we've done so far, where should my indices go? Down. I go get the right hand gesture. We don't want to speak up, but we got the hand gesture. Good. Like that. Right? So notice we have 2 upper indices and 2 lower indices. See the pattern here? Now here's the thing. Like when we think about the matrix A that we used upstairs, this was a thing that like inputs vectors and outputs vectors, right? Like matrix vector product. This thing like inputs 2 vectors and outputs a scalar. Would it make sense for me to like take a vector and multiply it by G? Like is that terribly meaningful if this is the only information I give you? Not really, right? Like I haven't told you what G is. It's like a thing that defines an inner product. There are ways to dualize these. I mean, obviously. If you want to be fancy about it, Riesz representation theorem tells you some way to kind of make these 2 pictures the same. But like, the reality is that we have matrices in both of these. These are 2-dimensional piles of numbers that are being used for very different purposes, right? And so that's why we have this kind of funny notation. And the way that we're going to distinguish is notice there's 2 lower indices here. So this thing sort of acts on 2 vectors because vectors are upper indexed, right? Whereas this guy up here acts on a vector and kind of outputs one, which you can kind of see from the pattern of the indices. This is a thing to get used to, but it's something we're going to start now. Okay? So anyway, this is the high-level point. That just, you can, matrices, just 2-dimensional piles of numbers, are used for a lot of tasks. And we often glue them together in undergrad linear algebra, and that's a mistake. Because like, if I just gave you a 5x5 matrix and said use this matrix, it would be very unclear for what. Yeah. I amused myself. Okay, so in any event, that's our basic setup here. Now, thanks to Einstein, one thing you might notice is that it's a little bit cumbersome to write all these sums. And there's like very few cases where that sum doesn't go all the way to n, right? And so starting back at Einstein, essentially what he proposed was to just throw that sum out. So anytime you see an index twice, the convention is that if the index is once upper and once lower, then there is an implied sum in your notation, like in this case over k. Does that make sense? Yes?
What's the alternative?
Just writing the sum. Yeah, it's cumbersome, but
You prefer doing that, or?
I actually often do, because I think when you do this, it's very easy to start writing expressions that don't make any sense. Yeah, especially like for instance, like if you start doing like product rule and derivatives and things, it gets real fishy really fast, right? Like if I differentiate this, the v's will get differentiated, but not the e's in some cases, and things get weird. I personally prefer to just write a bunch of cumbersome stuff, but maybe if I took another 3 remaining geometry classes, I'd change my mind. But I'm not going to because I'm old. Okay, but in any event, when you read research papers and textbooks, this is a convention that gets used often, so it's one we'll try to stick with. I may write the sums, but we will try to be careful about upper and lower indices. And Einstein had good reason for that, because it helps you type check. Like if I have an expression with like 2 upper k's and no lower k or something like that, then chances are it's wrong. And so there's like some clever type checking that's built into this system. Yes?
This is a matrix vector product, right?
Not really. So the e's are like vectors, and the v's are like scalars. So this is like a sum of scalars with coefficients in front of them.
Isn't this the same as taking like a linear composition of each of the k's?
That's right. So if you think of your matrix as a row matrix of v uppercase, then I guess this would be a matrix vector product. But we're trying to kind of separate you from that notation, because it's going to get clunky once you start having like 3 indices, right? Then you can't do that anymore. Yeah. Yes?
Is there a convention for when to pick, so for example, this could be E subindex K, E to the...
Yeah, so this is one of these scenarios where you have to make one convention, and then all your other conventions follow from it. So I think the original convention was that the standard basis has a lower index. And then because of that, the coefficients have to have an upper one. And then later on, we're going to talk about covectors, which are things that take dot products with vectors, and they're going to have upper indices. And we're going to see that it all works out in a really nice way. Yeah, that's the word I was looking for. But you're right. I mean, like, you know, if Einstein woke up and had put an upper index on E, then like everything would be flipped. At this point, if you did that in your geometry textbook just to be cool, you would throw everybody off. All right, any other questions? Yes, Artem.
Yeah, is it somehow related to covariant frequency variance?
Yes, yeah, absolutely. So vectors, what we're going to see is covectors, which are like things that act on vectors. They go together in a pair. And so like somehow for every covariant and contravariant thing, they kind of fit together in a clean way. We'll come back to that later. Yeah. But you guys are thinking all the right buzzwords, which is fantastic. Okay. So again, to summarize where we have so far, we have like one structure, one data structure, like an n by m matrix, but it's actually used for two different things. And that's A-OK. It's just important to call out that that's going to happen. OK, and we already wrote on the board these formulas here, so we can skip. Right, and as I've mentioned before, notice that this notation starts to give you a way to kind of type check and understand why matrices are different from one another, right? Like if I have something with an upper and a lower index, now I kind of have some intuition that it's a matrix that acts on vectors. If I have two lower indices, then maybe I have a thing that defines the dot product. Later on, we'll talk about an operation called lowering and raising the index, right? Cute, like, this is super cute. In differential geometry, they use sharp and flat. If you're a musician, you might recognize that as like, you know, raising and lowering a note. And exactly the way that they do that, for example, let's say that I had a linear algebra, or a linear operator that was defined by matrix A. I could define a dot product by saying, I want the thing that takes x and y and outputs the inner product of ax and y. And this object has two lower indices. And that's what like the flat operator is doing, for example. OK. Have I lost you yet? I'm trying. Ah, you guys are so quiet. OK. A tiny bit of terminology, because I'm likely to start using it. We're probably used to the finite dimensional picture upstairs of matrices and vectors. The thing that inputs a vector and outputs the product of that vector in a matrix is a thing we will call a linear operator. And as we've seen, these two things are dual to one another. So again, this is all a review of undergrad linear algebra. It's just in weird, annoying notation that's probably hard to remember. OK, fantastic. But notice, actually, one thing to kind of put in the back of your head is that like linear operators exist in spaces that are not Rn. So for example, you could think of the operator that inputs a smooth function and outputs minus its second derivative, right? That's an operator. You can check that it's linear, right? If I take the derivative of the sum of two things, that is the sum of the derivatives of those two things, yeah? So this thing satisfies all the axioms we've written down so far. Fun little quiz here. Can somebody name an eigenvector of this operator? Yeah. Cosine. Cosine. What's the second derivative of cosine? Come on, you're killing me. Come on. Somebody raise your hand. Help me out. What's the second derivative? Yes. Minus cosine. Notice I've conveniently put a minus there. So cosine has an eigenvalue of so close. 1, right? Because I took two derivatives and then I put a minus sign. Yeah, so I got the same function back. Can somebody name a different eigenfunction? How about cosine of like 2x? Yeah? What's the eigenvalue there? Oh, 4. Yeah, there you go. Anybody know what this operator is called in 1D? Rhymes with Laplacian. Yeah, this is the Laplace operator. And like the middle third of this course is going to be dedicated to analyzing this object and its eigenfunctions. OK. So now let's go back to reality. Of course, on a computer, all this fancy notation doesn't matter. A matrix really is just an n by m block of numbers. And the thing that we do a lot of is solve ax equals b. This in some sense is like an inverse problem, right? Like we're given the output of A, and we're trying to figure out the input that A got that gave you B. That was the worst way to phrase linear algebra ever, but I think you've all encountered this linear system of equations many times, so I'm not too worried about it. In this course, we will not be covering methods for solving ax equals b. We're going to assume that our code has built into it a means of doing that. I've included in the slides some pointers in Python on how to do such a thing. In MATLAB, it's \. if you're curious, you want some Google search terms, of course, the basic technique to do that is Gaussian elimination. There is one thing that if you do, because I teach numerical analysis in the fall, I'm actually contractually obligated. Ah, geez, now she's calling. Germany. That's not my mom. Right, so one thing that I think if you've only taken linear algebra class and you haven't ever touched a computer that you might do is like if I'm solving ax equals b and I have a and b, right, then like from linear algebra class, what would I do? I would invert a and then multiply it by b. And that's not a thing you should do. From a numerical perspective, it turns out that there are algorithms that solve ax equals b given both a and b that are much more numerically stable and efficient than doing the whole inverse and then storing. So if I catch you guys doing that on your homework, unfortunately you will not receive credit for that problem. And your laptop will probably melt down because we're going to have very large matrices. Sorry, if there's like one lesson you can get out of this course, is that you should be very careful inverting matrices. Interestingly, by the way, for those of you who are research students, there's a paper online that actually contradicts this. It says it's perfectly fine to invert your matrix, and from a numerical perspective, it might be equally stable. But in this class, that's still not true, because our matrices have really nice structure in them. So for example, we're going to solve a lot of problems where, like for instance, I have a graph, and like I have a vertex by vertex matrix, and there's only non-zero values for the edges. And like our graphs are going to be super sparse. So like, does it make sense to solve a bunch of, like store a bunch of zeros in my matrix? Probably not, right? Instead, I just like store a list of the non-zero entries. One thing you might know is if I invert a matrix that's sparse, it may not necessarily remain sparse. So what will happen, and I can tell you this will happen in your assignments, is like if you set up your linear system wrong and you invert your matrix, your computer will just crash because like you have order n entries in your matrix, but then order n squared entries in the inverse. So that's an example where like you really do have to use sparse linear algebra. Okay? Right, so again, essentially the point here is that like if you can avoid constructing a inverse, you probably should, although I've given a pointer to that caveat if you're curious to read a little more. The other thing to know in linear algebra, which we're only talking at a high level, we'll give pointers on the assignments when you need it, is just that the more structure you have, the better, right? Like there are fast solvers for very specific choices of A. For example, if A is structured with like ones and minus ones down the diagonal, it might be that like the Fourier transform is actually the right thing to do, which is of course for a very, very specific matrix, like this one. So like this is a great example of like, so here I've taken this differential equation, like the second derivative of f is equal to g, so like I'm given g and I want f. And I could approximate that by this linear system. Does everybody kind of see how I went from the problem here? Like 1 minus 2, 1 is kind of like the stencil of a second derivative. So I could write this as a linear algebra problem. If I take the inverse of this matrix, you'll see that it's dense. You should put that in MATLAB if you don't trust me. This is a very structured matrix. Notice it's tridiagonal, it's sparse, it's mostly zero. And so the more that you can build that into your code, the better. And we'll see many examples of this in this course. And it's not just for like one-dimensional stuff. For example, this teddy bear, when we compute its eigenvalue, so we're hitting it with a hammer, we want to know how it vibrates, which we will do in this course. The matrices are going to have one entry for like every vertex or something, and one non-zero only for the edges. And notice there are far fewer edges than there are vertices squared. Okay, so I've made the same point about 75 times, and that should help you realize how important it is. Okay? If you want to read a little more, I've given you some pointers to different linear solvers. In this class, again, it's going to be a black box, and that's what we need to know. So here, if you find yourself implementing a sparse linear solver, unless that's your course project, which there are some really cool course projects that would like involve like, can I come up with really fast linear algebra specifically for graphs or meshes or something is a cool problem to study. But if your project isn't on that and you find yourself coding Gaussian elimination, probably something has gone wrong. So come talk to me. And be sure to use sparse matrices. Any questions about that so far? I'm rushing a little because I want to get to the calculation that's hard and I never end up with enough time. Okay. The other part of background material we're going to need in 68410 is the little optimization piece of the puzzle. We're going to use that starting in our next lecture because we're going to talk about like curves and shortest paths and curvature and all that kind of stuff. And so in particular, we'll remind you of a few terminology from optimization, and then we're going to do something that's probably new to most of you guys, which is how to compute a variational derivative, or a ghetto derivative, if you like. Okay, as an aside, you might brush up on matrix calculus if you haven't seen it in a learning class. We're not going to use it too much in this course, but this is just a useful piece of machinery that you might not have encountered before. Okay, so in case we've never encountered an optimization problem before, they tend to have a form like the following. You're going to minimize or maximize some function subject to constraints. So for example, maximize profit subject to only using the materials that I have in my warehouse, anything like that. So typically, my function f will be an objective or an energy. My constraints split into equalities and inequalities. One thing that's worth pointing out is that this is super generic language. So for example, let's say I want to solve ax equals b. Of course, if I made f of x equal to the difference between ax and b, right, the minimizer of that would be to find an x that satisfies that system. Does that make sense? And similarly, it turns out we'll actually justify in a minute that like you can write down eigenvalue problems this way, root finding. Like, there's this huge class of computational problems that all can be written in the form of the green box on top. That's the point. And that's really the case in geometry as well, which is why this is such a powerful language. Now, what does that mean? If I give you a piece of software and I say like, you give me f, g, and h and I'll give you the minimum, like how well, and that's all I know about the software, that's just its job in life, like how well do I think that software will perform? Well, so we can write like traveling salesman problem, for example, in this notation pretty easily. What are some other good ones? Steiner points. Weirdly, I'm struggling to think of NP-hard problems. What was that? Bagpipe problem?
Yeah.
Knapsack. Oh, interesting. Bagpipe, maybe in Russian. Yeah, so essentially, this is super generic language. So you should not trust a piece of software that can advertises it can solve any one of, any instance of these problems. But of course, writing things in this language can often provide a lot of insight. When we study optimization, of course, the main object that we work with is a gradient. We can think of a gradient, by the way, as sort of like a vector of little operators, like these d over dx's. Notice I've been really, if you really want to wrap your brain, including when I wrote the course notes for this class, if I have d over dx and I have an upper index, but the upper index is in the bottom of a fraction, I never can convince myself where it should go. But I think I've managed to get it right. But in any event, the gradient is just the thing that inputs a function and outputs all of its derivatives. And as we know, this is the sort of schematic, right? It's the gradient points uphill. So if like black is a high value, I guess, and white is a low value, then it will point in. I'm moving fast because I'm assuming this is review for most of you. But again, I'm going to keep reminding you, if you have a question, you should stop me. OK. Similarly, if I have f is a map not into scalars, but into Rm, then I can write this object called the Jacobian matrix, which is just the derivative of every possible component of f with respect to every possible input of f. Notice that Jacobian matrices, what do? They like take vectors in one tangent space, then they kind of map it to another tangent space. I think the filming just died. No, it didn't. OK, whatever. I think, again, it's your responsibility what happens in this room. So what does that mean? The Jacobian matrix it's like a matrix that acts on vectors. And notice we have one upper index and one lower index here, right, which is just the notation we used up there. Yeah? OK. We're also going to use one more object called the differential, which is something you probably saw in multivariable calculus but might not have thought much about. And this is a directional derivative. And it's basically just a change in notation from the previous couple slides. So let's say that I have a function f. I'm at a point x naught, and I want the derivative of f at x naught in the v direction. Did that phrase parse? That was a lot of words. Then I could write that pretty clearly in this limit form here, right, where I like take a little perturbation of x naught in v direction, and I compute derivative in 1d. Does that make sense? And one thing that you can check very easily, you can use Taylor series or any number of other arguments, is that there's this expression down here for df, which is that it's really the dot product between the gradient and v. In fact, in differential geometry, we usually start with d and then derive a gradient. But in calculus class, you do the opposite. OK? So what this df notation, notice, is just kind of like an inversion of the notation on the right. That's really all that's going on here. OK? so quiet. Shrug. Okay. Right. So yeah. So that's the object we're going to work with, and notice that like this object is going to be really central to optimization because what is the df operator at a point x0 that minimizes f? Yeah. 0. Thank you. See, only the undergrad is answering questions here. We've got all these PhD students, and they're all quiet. That's right. So df is going to equal 0 exactly when I'm at a minimum point here. And then, of course, we also have the Hessian matrix. We actually will not encounter many Hessians in this course, but that's the matrix of second derivatives. The only reason I included it here is just to continue to think about our notation. Remember that Hessians usually kind of appear in a quadratic, like Taylor series. And notice that there's 2 lower indices here. Unlike the Jacobian matrix, where there was 1 upper and 1 lower. I'm just trying to help you pattern match today. That's my goal. OK. Fantastic. So what do we do when we optimize? Typically, we take the gradient and set it equal to 0. One way to understand what we've done here is essentially we've converted an optimization problem into root finding, right? Like we're trying to find the zeros of the gradient of a function. You can do a similar thing with Lagrange multipliers if you have an equality constraint. So for example, let's say I want to minimize a function f subject to g equals 0. Hopefully this phrase makes sense. By the way, st apparently is subject to. I got a negative textbook review because I used the phrase such that, and apparently, like, God forbid. OK, so here's the kind of schematic for how to understand this. So here are the level sets of f. So like, as we move in, f is getting smaller. So if I minimize f without a constraint, I end up at the center of this target here. But of course, I'm constraining myself to move on this curve, which is like all the sets where points where some other function g equals 0. Does this picture make sense to everybody? And so one thing you might not have thought about is like, where did the Lagrange multiplier condition come from? So we can think of minus the gradient as like the downhill direction, right? Like, so if I have a function, I can be minus its gradient, and I point my toes in that direction. That's the direction I can walk and go down, right? This is why gradient descent works. OK? But if I have a constrained problem, I can't do that, right? I'm constrained to walk along this level set, right? So like grad f equals 0 is no longer the right condition. I need a new one. But essentially, what we can figure out is like, what is the gradient of g? Well, if you think about it, it's orthogonal to the level set, right? Remember, gradients are perpendicular to level sets of functions. So the picture looks like this, right? So grad g points away from the red curve. And that's the direction I'm not allowed to walk in when I do gradient descent, right? I have to walk along the curve. So when am I at a stationary point? Well, if you think about it, the picture to have in mind is the following. Essentially, here's the minimizer with the constraint, because grad f, or minus grad f, is telling me to walk this way. But that direction is parallel to grad g, meaning the only direction I can walk is the one that makes my constraint change, right? A different way of writing down, I see, I'm going to finish my sentence. A different way of writing that 2 vectors are parallel is to just write that grad f is equal to lambda times grad g. And that's exactly the Lagrange multiplier condition that you've probably seen in calculus class. So I think it's actually pretty intuitive. You might have just like had somebody write it down, but it's a nice schematic here. Yes?
What if you're constrained to sort of like an offset ellipse thing and you have 2 points where...
Oh, you mean like maybe you have a saddle point or something like that?
Is that a saddle point?
You have an ellipse.
It's like if this red thing was an ellipse, that was...
If the red thing were an ellipse. I think you're still good, right? So the gradient would still point inward.
Yeah, but you have 2 points where the gradients are parallel.
Oh yeah, this tells you nothing about uniqueness. This is just saying locally there's nowhere I can move to make the function smaller. Absolutely. And as we know, many functions have local minima and global minima. And just because, for example, if f is convex, but g is not, then you might still have multiple minima. That's one example, I think. Yeah. Actually, sorry, g in that case is convex, but the 0 level set is not. But we'll come back to that later. Fantastic. Any other questions? Cool. So again, what do we use Lagrange multipliers for? It's again taking now a constraint optimization problem and turning it into root finding. But now it's joint root finding between x and lambda, right? So we've kind of raised our problem with one variable, but now we can find it like zeros of this system of equation, and that's equivalent to finding local optima to this problem, not necessarily global. By the way, maxima also satisfy this. Yeah, so you be a little careful. So as a quick example for fun, I don't think I'm going to do it because I'm rushing to the example that I want to have time for. Let's say that F is equal to X transpose AX, so it's kind of like an inner product. And G is equal to the norm. That should probably be norm minus 1, by the way, because constraining the norm of X to equal 0 is not a very interesting problem. Somebody remind me, and I'll fix that in the slides later. So in other words, the optimization problem I wanted to write was min X transpose AX subject to the norm of X is equal to 1. Right, so there's a minus 1 missing here. My apologies. Then, right, so if I just plug in the Lagrange multiplier condition, the gradient of F is equal to 2AX. The gradient of G is equal to 2X. If you're not confident in these expressions, that's fine, but you should check them at home. So what is the Lagrange multiplier condition? It's AX equals lambda X, which is a phrase we all have said 1,000 times while we brush our teeth in the morning. It defines what kind of an object. You're all whispering. It's really funny. I can see your mouths move, so I know you know the answer. Eigenvalue. So lambda would be an eigenvalue, and X would be on 3. 1, 2, 3. Thank you. Okay. So this is yet another way to understand eigenvectors, is that they're like local optima of this particular optimization problem. Yes?
Wait, so for the fixed constraint, what would G of X be?
G of X would be the norm of X minus 1. Notice I forgot to minus 1
Does that
here.
have the same gradient?
It does. Well, notice that if the norm of X were 0, it still satisfies AX equals lambda X. It's just a really boring X and a really boring lambda.
So
Yeah.
it seems like you can solve the problem, but the problem doesn't know what you're constraining.
You're right. There are multiple problems that have the same optimality condition. This is a really tough philosophical thing. Notice if I put like a 75 here, it would also satisfy that condition.
Okay.
Yeah. I'll let you philosophicate about that later. Absolutely. Good question. That's right. Eigenvectors also can scale up and down, right? Yeah. Any other questions? Glad you guys are thinking critically. That's great. That's exactly what we should do. Okay. Unlike in previous offerings of this course, like if you find the videos online, they will contain all the same typos because I managed to not notice. The last time I taught this class was in a weird, sad, empty classroom with no lights on because it was pandemic, which explains why I didn't notice the typo, but I should have caught it this time. Sorry. But in any event, in the course notes, there's lots of details to read involving justifying these Lagrange multiplier expression a little more carefully. And if you're curious, although in this course, it also talks about KKT condition, which is what you have to do when you have inequality constraint. Okay. All right, but what I really wanted to spend my time on today, and what is like my favorite thing to teach people, because it's like something you should all know, it's like a good life skill, and it's missing from most of our students, is variational calculus. So just out of curiosity, have you guys computed first variations of functions before? A few of you have. I know some of them in my office. Right, so essentially, here's the high-level point, is in geometry, the unknown variable is very rarely a number. It's usually like a shape or a function, right? And so the calculus machinery we've developed so far doesn't quite extend to that case, right? Like we know how to minimize a function of like a finite set of things, but like what does it mean for a function to input a curve and output like is this curve the shortest curve, right? And so that notion is part of a larger area of math called variational calculus, where basically the point is to want to take calculus and apply it to spaces that aren't just like points, okay? That high level kind of motivation makes sense? So essentially the object that we're going to work with in variational calculus, like scary notation alert, it's going to happen in like t minus 8 seconds, is a particular object we call the Gâteau derivative. Sometimes people call this the first variation of a function. Sometimes they call it, what are some other names for it? Like the Euler-Lagrange equation. This all means the same thing. Does this expression look familiar from the previous slides at all? Notice I have a function u, then a second function psi. I'm taking u and I'm adding a multiple h of psi to it, right? So I'm kind of like perturbing it in the psi direction. And I'm taking a derivative at t equals 0, right? So this is kind of like that limit I wrote down before. So abstractly, this thing is kind of like the directional derivative of f at u in the psi direction. Does that phrase make sense? But what is f? F is a weird object now. This is an object that takes in like a function and outputs a number. So think about like if I want to compute shortest path between 2 points. F would be like a thing that inputs like a curve and outputs its length, right? Everybody with me so far? This is an abstract notion here. We're going to do like a concrete calculation with a minute, and then I think it'll make it a little bit easier to understand. Okay. So, yes.
What does it have to do with K?
What does it have to do with K? Is this like a, oh, cake, I was going to say, is this like a weird passive-aggressive way to tell me I made a typo? Yeah, gâteau means cake. I think it's actually someone's name, but I could be wrong. I don't know. Check the Wikipedia page. Good question. Every year I get that question, and then I forget. Yeah. Right, so this object is gâteau derivative. I think usually when you take variational calculus, you derive something called Euler-Lagrange equation, which is sort of a formulaic way of deriving this thing. But this is one of those formulas that I find is just easier to derive by hand every time I need it, rather than remember how to apply Euler-Lagrange equation, because I always get that wrong. But that's on you guys. So I thought rather than belaboring the theory of these objects a whole lot, we just do calculation with one of them so you kind of understand how this stuff goes. Okay? Now in this class, you are perfectly welcome to blithely assume that all functions are smooth and differentiable as many times as you want. You can exchange integrals and derivatives at will. You have license to do all of these things. And your professor, who is far, far away from the math department, will shield you from any criticism you get from course 8, 16, 12, whatever it is. Okay? So I thought for the last like 25 minutes of class here, essentially we would use variational calculus to derive a formula that we may have seen in other parts of computer science, namely the formula for a cubic spline. Now, those of you who took 64400 or 6837, depending when you took my undergrad graphics class, have seen exactly this formula before. And it's the basic machinery people use to interpolate between data. Anybody know where the term spline comes from? You do, you took my class, yeah.
Yeah, it's from ship makers who
Yeah.
make these little wooden curves and then they put specific points on there to make it sure it's shaped right.
Yeah, splines come from woodworking and shipbuilding. So a spline, and by the way, like there are terms like knot when people talk about splines, which makes sense if you think about a piece of wood. Literally, to make a spline, one way to motivate this system we're about to write down is you take a very thin piece of wood and you put little nails in it, and you can determine the tangents to this thin piece of wood by kind of rotating it about those nails. And the equilibrium shape that that thing will have is a cubic spline. I'm not a physicist, so I won't even bother trying to write that problem down. But instead, we can motivate it in a different fashion. And that's an interpolation. So let's say we want to solve the world's least interesting, I'll call it machine learning, because we can be trendy then, okay? So in particular, here's our machine learning problem. I have a function f of one variable, we'll call it t, okay? And I give you 4 pieces of information about f. I tell you the value at t equals 0, call it a. The value of f at t equals 1, call that b. The derivative of f at t equals 0, we'll call it c. And the derivative of f at t equals 1, we'll call that d. So does everybody understand the picture here? F is like some green function here. And I know its value and its slope at 2 points in time. And my task is to find a reasonable, or notions of reasonable TBD, interpolant between these two things. Cool? Nods? Acknowledgement? Something? Okay. So this becomes a design problem, right? I can design any f that I want, but if I'm thinking in terms of optimization, I might write down an objective function that says, well, it has some constraints. I know that f has to go through 2 values and 2 slopes, and I can choose any f in between those 2 things, right? And so I need an objective function to decide like what f's are good and what f's are bad. Yeah? Now, one thing you might do is say, well, like what would be a really good f? A really good f might be one that's flat, right? And flat things are lines. And what do we know about the second derivative of a line? Somebody new, raise your hand, contribute. Yes? 0, that's right. Linear things have 0 as their second derivative. But unfortunately for us, we not only specified 2 values, we also specified 2 tangents. And what else do we know about a line? Does it have to have, like, can it have 2 different tangents at 2 different points? I'm not asking deep questions today, guys. No, right? Like lines, they don't look like curves. Okay? So one optimization problem that we might write down, at least abstractly, might look like the following. I could say, I want to minimize the norm of the second derivative integrated from 0 to 1, subject to the 4 constraints that I've written here. Notice if the minimizer were 0, I got a straight line. That make sense? So this like feels like a reasonable modeling thing to do, but if I told you to like use calculus for this problem, it's not obvious how to do it, right? Because f is a function, right? I don't know how to take derivative of this weird integral thing. And that is what variational calculus is for. And I'm talking too much, and I'm almost out of time. So let's actually do that. Notice I've used the phrase cubic spline, so you can probably guess the end result of this calculation, which is going to be that f is cubic. All right. Can everybody read this board? I know it's kind of messy. I don't like this classroom. Did I mention that? Okay. So here's going to be the picture we have in mind. Let's say that I want to minimize. Let's have a little schematic on the side. We want to minimize some function g of x. In this case, we're going to see the boundary the constraints don't actually matter a whole lot. Let's say I want to minimize a function g. Notice, like, and let's say we're in the finite dimensional world. One thing we could have done is take the gradient of g and set it equal to 0 at x, right? Notice that that is the same as the gradient of g at x dot product with the vector v is equal to 0 for all vectors v, right? This is just saying 0 is the vector whose dot product with any other vector is equal to 0. Everybody with me so far? This feels circuitous because it is. But we're going to end up at an expression that makes sense in this case over here, okay? But this thing, remember, is the directional derivative, right? So a different way to notate this is that 0 is equal to d over dh of g at x plus h times v evaluated at h equals 0. I want you to take a second to digest this notation because it's ugly. Does everybody understand the equivalence between these two things? Beyond moving the 0 to the left. We all agree that these quantities are equal? Nods, acknowledgement, something. Help your instructor out. Okay, fantastic. Here's the thing. We're going to find that this expression on the bottom, this is going to be the one that we can adapt to this infinite dimensional case. Right? Because notice that this is kind of a one-dimensional problem now, right? Like x is a vector, but now I'm kind of just looking at the slice of x through v. So like a picture you might have is like maybe these are the level sets of my function. Here's x, which is the minimizer. I choose some arbitrary direction v, like that. And then I kind of plot, you know, h f of x plus h v, like that, right? Oops, I switched from f to g, sorry. That's a g. And if it's a minimizer, then that like 1D slice looks like that, right? That's essentially what this formula is saying. Everybody with me so far? I'm repeating a lot because this is one of these calculations that I think is easy to agree with, and then you try to do it, and you're like, ah, you know, like, I think. Okay. So now we're going to operate in analogy to this computation, but on this infinite dimensional problem. This is exactly what you're going to do on your homework, so you should perk up. Okay. So, and I've got it on my notes, but not these notes. These notes. Okay. Wouldn't it be great if we had like multiple boards that we could use? So let's draw a schematic, and then we're going to make it into math. Yes?
Are there any assumptions about the family half that we're?
Many, and we haven't written any of them down. So we're going to, in this class, we'll just assume everything is infinitely differentiable and justify a posteriori that that's OK. That's right. And in this class, we're not going to talk about existence of a minimizer, which is a really important thing to prove if you're in math. But we're like closer to the physics perspective, where by physics I mean sloppy. Yeah. OK, fantastic. So let's say, here's our picture here. Right, so we've got 2 points, we've got 2 tangents. There's our curve, something like that. With me so far? OK, so this is our function f of t. Yeah? And essentially, if we think about this expression here, and we try to make an analogy, what it might be is that like maybe you're some adversary and you insert some little perturbation like that. You know, some like P of t, which is gonna like take f and like you're gonna be evil and add a little bump to f. And what do you want to show? You want to show that if I add that little bump to f, my energy got worse, right? That's sort of the schematic to have in mind here. Yeah? Now, we need to be careful about our boundary condition. Let's say that f satisfies the boundary constraints. Can I just add an arbitrary perturbation p? No, p needs to satisfy a few things. It needs p of 0 equals p of 1 equals 0, and p prime of 0 equals p prime of 1 equals 0. Do you get that? Because now this is going to leave the boundary values and derivatives alone. Okay? Notice our proof is sort of going in the forward direction. We want a much harder proof. It's going to be the reverse direction, like showing that if you satisfy that, you know, yeah. Okay. So what we're going to do is say, like, if I take f, I can make a whole sequence of, a whole set of functions, right? I could look at the following function, which is f of t plus h times p of t, right? That's another function if we think of it as a function of t, right? And I'm going to think of there being a one-dimensional function of h where I evaluate this objective at this thing, right? And if f truly minimizes this quantity, then the derivative with respect to h of that whole complicated expression should be 0. And I'm going to just keep rephrasing the same thing in different forms. Okay? So let's actually do that calculation. So in particular, we're going to take the first variation, dE, at at f in the p direction. That's one way to write this notation. Notice that this is like the differential, right? It's like the differential of e at the function f, right? Because that's the one that we think is the minimizer in the p direction. And what is this thing? So from our what we've already written down, this is d over dh of e of f plus h times p, evaluated at h equals 0. Right, that's just the expression we already wrote down. So again, do you see, again, this is a directional derivative. So like f and p are like vectors and h is like a scalar. And keep reminding you because it's hard to remember this stuff. Okay. So from here on, we're just going to do calculus. Yeah? So let's sub in, so what is our form for e? So in particular, this is d over dh of the integral from 0 to 1 of. Now we have to be careful. This thing inputs a function and takes a second derivative with respect to t, right? Here it input f and it gave this expression. Here we're inputting a new function which is f plus hp, right? So the second derivative is going to be f double prime of t plus hp double prime of t squared dt at h equals 0. Everybody see what I did there? Notice there's two letters at play. There's H and there's T. This is going to get annoying. Count to 5 here. Thumbs up. Good, 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 good. So this is great because now this looks like calculus. I don't have to worry about all this abstract nonsense, right? Now I just do calculations. So in particular, the integral is with respect to T. The derivative is with respect to H. So we can safely, in quotation marks, move this derivative inside. Right, because they involve two different letters. So let's do that. So in particular, this is equal to the integral from 0 to 1 of 2 times, this is the product rule, I believe, f double prime plus hp double prime of t times the derivative with respect to h of this interior expression, yeah, which is equal to, you said it. Let's say it louder.
P double prime.
Everybody say it. Thank you. P double prime of t evaluated at h equals 0 dt. I warned you it's a little messy. Okay? But it's about to get really pretty, I promise. Okay? Because take a look. We only care about h equals 0, right? We don't really care about the derivative of this slice away from the minimizer. So now let's substitute in h equals 0. So this term goes away, and we are left with 2 times the integral from 0 to 1 of, I forgot what I was doing, f double prime of t, p double prime of t dt. No h to be seen. Cool? Oh, perfect timing. This is great. Only a few phones out, so I have most of your attention. Okay, so here in this expression, we see the product of two things, both of which is differentiated. What does this scream out to do? Integration by parts. Thank you, phone guy. I'm just giving you a hard time. This is my job. If I haven't embarrassed at least one student by the end of lecture, I've done something wrong. Okay, that's right. So anytime you see the product of two derivatives, it's screaming out to you for help that you should integrate by parts. And in particular, we are going to move all the derivatives onto f, and we'll see why in a minute. Okay? In fact, we're going to have to integrate by parts twice, which is part of the annoyance of having put a second derivative here. Okay. Now I erase for another 20 minutes, and then we continue our calculation. So. Okay, there's an expression up there. Now we integrate by parts. I'm going to move the derivative from p to f. So if you recall, that's going to do the following. So you'll get, I guess, 2, let's see if I can do this without my notes, f double prime of t, p single prime of t, evaluated at 0, 1, minus the integral from 0 to 1 of f triple prime of t, p prime t, dt. You guys are closer to calculus class than I am, so you tell me, did we do that right? Cool. What is this value? 0. Remember that we just, by ansatz, by fiat, we decided p prime of 0 and 1 is equal to 0. Yeah? So this is looking tidy. Now what are we going to do? Integrate by parts again, yeah? Okay. So what do we get then? So now we're going to get minus 2 f triple prime of t, p of t from 0 to 1 plus the integral from 0 to 1 of f fourth derivative of t, p of t, dt. Okay? Notice I have to be careful with the minus and the plus because we did it twice. Okay. What is this value? Also 0, right? Because we just defined p to be 0 and its derivatives to be 0 at the endpoint. We can take p to be anything we want, right? It's just a perturbation, and we have made that assumption. Cool? Cool. Okay. Now, let's say that f is a minimizer. Like f actually minimizes the energy E. This is where our a little mathematical leap of faith is going to happen, also known as gaping hole in Justin's theory. Okay? So f minimizes this energy E, and we just took the derivative of E at f in the p direction. What do we know about this integral then? What do we expect to happen? It should be 0, right? Because what is a minimizer function? It's a thing where the derivative is equal to 0, right? So we expect this to be 0. Does that make sense, the little argument I just made there? Again, like if you're doing this mathematically, you have to be a little bit careful that like a minimizer even exists. We're aligning that right now. Okay? Did we put many assumptions on p? P could be all kinds of wild and crazy stuff. It could be like a cosine. It could be like a delta function. It could be whatever. No matter what I get 0 when I take this integral. Right? So in particular, one thing to think about, you may have encountered like an electrical engineering course, is something called Dirac delta function, which is sort of like you take a sequence of functions that get like pointier and taller at a given t. And I could like take a whole sequence of these things at p that eventually just kind of pick out the value of f at a given location. Where do you think I'm going with this? So this integral is equal to 0 basically for any choice of p. So in particular, what must be true? I don't know. Where are you?
Fourth derivative must be 0.
Yeah, this thing had better equal 0. Right? Because no matter what I took its inner product with, I got 0. Yeah? You should be really excited right now. So what did we do? We just said we want to minimize this energy with respect to a set of functions. And we just learned something about any function that minimizes it, namely that the fourth derivative of f with respect to t is equal to 0 for all t. Is there any p in this expression at all? So do you get how like the gâteau derivative here is just like a transitory object? It's just to get us to like some PDE. Isn't this cool, this calculation? I started with an optimization problem, and I ended with a differential equation. A really simple one, because this is an easy problem, but a differential equation nonetheless. That make sense? So that's what variational derivatives are useful for. They take optimization problems over functions, and they convert them into things like this. Just the same way that like taking gradient setting equal to 0 of a function converts minimization to like root finding, right? There's like kind of a similar duality here. Now, just to conclude our story here, what is a function whose fourth derivative is equal to 0? Somebody said 0. No. That is sufficient but not necessary, would be the polite professor way to answer that.
Polynomials, right?
Yeah. I could integrate this 4 times, and I get a cubic polynomial, right? So in other words, we just showed, at least in the interior from 0 to 1, the f of t is like a t cubed plus bt squared plus ct plus d, like that. Notice we have not solved our optimization problem completely because there's still 4 unknowns, but 4 is a heck of a lot less than infinity, so we're doing pretty well.
Same A, B, C, D as the original.
Oh, I chose really bad notation. No, they're not, and that's a great question. Actually, of all the people in this room, the students in my undergrad graphics class should know that I should have chosen, I don't know, Q1, Q2, Q, that was a Q, 3, 4, right? They're not the same A, B, C, and D. However, there are 4 degrees of freedom that I don't know here. And I have 4 pieces of information about F, so I can do a little bit of linear algebra to recover those 4 things. Yeah? And that, at the end of the day, is a cubic spline. Yeah? So what did we show? To step back 50 feet. We started by saying we want to minimize the total second derivative. You may recognize this. Sometimes computer graphics people call this the biharmonic energy of F, if you want to be fancy about it. But in any event, we said, OK, if F minimizes the biharmonic energy, subject to these boundary constraints, then it must be a cubic function. That's what we showed. Isn't that cool? Yeah. Risham.
It looks like when we've been looking for f, we assume that it's 4 times differentiable.
That's right.
So I guess, are there other solutions that are not 4 times differentiable?
Yeah, so that's a fantastic question. So the question, in case you couldn't hear it, was like, OK, but we put a lot of assumptions into the proof here. Proof is in quotation marks, right? Namely, what are all the yucky things we did? We like put derivatives into integrals. We assumed that f exists, which it may not necessarily, and that we can just differentiate f and p at will, right? And you're right, those are all bad assumptions to make. And to go back to the question from the back of the room earlier, indeed, you really should be careful about like what class of functions f is in. It does turn out that what we've done here is kosher, and I encourage you to flip open, what's a good variational calculus textbook? There are many where you can kind of look at like, what is the class of functionals that you can build out of f and its derivatives that like have okay solutions to this problem. Generically speaking, when this is smooth and convex, you're usually okay. But that is not a thing that we've checked. Indeed, you need to be really careful to show that there exists an f that minimizes this and that it's differentiable. So for example, if you wanted to break that, there's a very easy way, which would be to replace the square here with absolute value. And then you'll see, like that's like total variation style things tend to have like solutions where like as you have a sequence of f's that get closer to the minimum, the solution like begins to develop a shock or a singular point or something. So there are absolutely classes of problems that are what we would say ill-posed. But this is not among them. And in this course, we'll typically assume that like everything is differentiable and smooth and well-behaved. Yeah. Certainly on your homework, you don't need to justify that a minimizer exists. Yeah. But it's a great question. It's exactly the right one to ask. Yes?
Why isn't the solution just you extrapolate those tangents and at some point they meet? Because those are like very linear, right? Like they're.
That's a fantastic question. Actually, it's related to Artem's question in some sense. So the proposed idea here, if I understand correctly, is you take these two tangents, you kind of extrapolate them like straight lines, and they meet at a point. First of all, what is the second derivative of that? Now it's infinity. So for one, it would be hard to evaluate this objective function. But you could ask a slightly different thing, which is you could say, maybe there's a sequence of smooth functions that approach the one that you have described. So now they are smooth, and I can evaluate this thing. And I could look at the sequence of E values. And one thing that you'll show is, for one thing, that has to diverge. Like, you can just try it and show that that's not the right answer to this problem. But moreover, rather than doing that a posteriori for like whatever function you cooked up, really the theory that we're missing in this class is one that shows that a smooth function exists, right? So what we've shown, to be very precise, is if a smooth function f exists and minimizes E, then it must satisfy this expression. But that first half is trickier to verify. Absolutely. Yeah. Mm-hmm.
So what if you have like multiple points? Can you just do that like piecewise locally, and then would you get the right solution?
You would, yeah. And you can justify that to yourself at home. Yeah. A different thing you might ask, which if you want to get yourself really confused, now I'm saying all the things which are going to insert doubt into my lecture. I should just leave them out so you feel better. If you put the first derivative here instead of the second, then what you'll end up showing is that f is linear, but that's not enough degrees of freedom to satisfy all the boundary conditions. And you can basically convince yourself that problem is ill-posed. So that's an example of a kind of innocent-looking one where the boundary conditions are incompatible. So this is definitely a shaky house of cards we've got here. But this perturbational argument that we've made is perfectly kosher. Notice that linear functions still have fourth derivative equal to 0. It's just that one doesn't exist that satisfies all the things you want. So this math is perfectly fine. It's just the existence question is a little tricky. Yeah. All right. So do we understand the calculation we've done and its limitations? That's what we're after at the moment. Yes.
Can you do something similar for points in 3D and tangential planes?
And tangential planes.
Yeah. So, like, for instance, if you have point cloud and you want to like do this cubic splice.
Oh, I see what you're saying. I think you'll end up with something very similar to what people call Poisson reconstruction, but with a fourth derivative in it. I'd have to think about it. It's a good question. I don't know. You should be a little bit careful with boundary conditioned isolated points, but that's a PDE technicality. Yeah.
Isn't this subdivision surface like just doing the same thing in 3D?
Possibly. But this seems like a great niche question for the two students who are my own students to discuss with each other. And any other maybe broader applicable questions I can answer to everybody here. All right, fantastic, folks. So I'm glad that for the first time I've given this lecture in 7 years of being at MIT, we actually made it to the last slide. But this little calculation is probably uncomfortable. It's the kind of thing you have to look at a bunch of times and convince yourself is okay. And obviously there are corners where it's not. But you're going to have a lot of practice with it on your homework. And later on in this course, when we motivate the Laplace operator, we're going to do exactly the same thing about 75 more times. Okay? So with that, get started on your homework. Make sure to download the latest file. If you have the old file, please delete it. And I will see you all on Tuesday. Have a lovely weekend. Let me close this thing.